Hello, so we are now with activity 1.8 amplifier models, and we are asked to draw the amplifier models for 1, the voltage amplifier that we have already been working with, 2, the current amplifier, 3, the transconductance amplifier, and 4, the transresistance amplifier, and then we have to define their gain parameters, meaning the open circuit voltage gain, the short circuit current gain, the short circuit transconductance gain, and the open circuit transresistance gain. So let's do that. So voltage amplifier. So our model for the voltage amplifier includes an input impedance, Ri, where we sense an input voltage, Vi, and then we have a voltage control voltage source, this is ground, connected to the output resistance or the output impedance. And the voltage that we get across this voltage control voltage source is AV or AVO, open circuit if you want to call it, times the voltage at the input. So the amplifier is this part. We sense an input voltage, we amplify it, and we produce an output voltage. Now, the open circuit voltage gain, AV or AVO, I defined it here, is defined as the output voltage over the input voltage. Remember, when the circuit is unloaded, how can we say that? Well, we can say it in two ways. One, we can say that the output current, I out, is equal to 0, meaning there is not going to be a voltage drop across the output resistance because the current is 0, and so the output voltage is the same as the voltage that you have across the voltage control voltage source. Or equivalently, you can say that RL, the impedance of the circuit that you will connect as the load, is equal to infinity, which is, in both cases, this is equivalent to disconnecting the load. Okay. Now, in this amplifier, the ideal characteristics, says here, also identify the ideal values of Ri and Rout. We want an Ri, which is infinity, and that's because if we have an input impedance of infinity, the input current, II, will be 0. We are not drawing any current, therefore we are not going to have any loading effects at the input stage. And similarly, we will want our out in the output to be equal to 0, because like that, we do not, once we connect a load, we do not have a voltage drop, we do not have loading effects, or we will be able to maintain a stiff output voltage independently of the load. The load could be very small, and we will be able to do that. Or the amplifier will be able to do that. So those are the ideal parameters for the voltage amplifier. Let's do another type of amplifier. By the way, when do we use a voltage amplifier? We use it, for instance, to model op-amps, to really model any voltage amplifier circuit that we will create in electronics. Typically, these circuits, you have an input voltage that you are amplifying. And functionally, what you're going to care when that is interfacing with other parts of the circuit is, number one, what is the input impedance, number two, what is the output impedance, and number three, what is the open circuit voltage gain. And then, well, there is a circuit that is implementing that. So current amplifier. So in this case, what we're going to do is at the input, we also have an input impedance, and we are sensing the input current here, I. So you have a network where you're sensing an input current. And then you have a current control voltage source, a current control current source. So you sense this current and you produce another current, and we are going to model it, which is Norton equivalent. So we have the output impedance there, R out, and this is again IS times II. And we are producing an output current, output voltage. Here we have input voltage. Okay, so once again, we sense an input current and we produce an output current that is a scale version of that input current by the factor of the amplification factor, AIS, and we have an output impedance. Now, how do we define AI? And this AI stands for the amplification of the current, as opposed to V for voltage. And in the previous one, I say AVO for open circuit. In this case, we are doing AIS, because this is a current amplifier. The ideal conditions is you are testing this when the output is short circuit. So maximum output current, in this case, if you short circuit here the output, these two nodes here and here, right? You short circuit that, is where you have the maximum amount of current going to the output node, or are out, not drawing any current. Similar to in the voltage amplifier, to have the maximum voltage, you will need to open the circuit. So this is defined as the output current over the input current when the output is shorted, or the short circuit current gain, right? How do we define that? Well, we could say that the voltage output is 0. That's the same as putting a wire between those terminals, or equivalent that the RL, if we connect a load there, is equivalent to 0. Now with that, what are our ideal parameters in the case of a current amplifier? So in a current amplifier, you want to get this input current, right? Ri, instead of being infinity for the voltage, you do not affect the input current if the input impedance is 0. And the same thing, the R out in this case, because you want all the current, the output current to go to the load, as opposed to the output impedance, you want R out to be equal to infinity, as large as possible. Just the opposite as the voltage amplifier. Now, this is a current control current source, right? And we use it to model any current control current source, any current amplifier, current input that you amplify. You use it in one model to model actually the bipolar junction transistors, where you say, I have a base current that is small, and that results in an amplified collector current that is larger. So you can use it to model transistor circuits. Let's do the next one, the transconductance amplifier. So in this case, we are going to sense at the input, you have a voltage across an input impedance and the output is a current amplifier. So you have a current source here. This is the input voltage. There was a typo there. Okay, so in this amplifier, we sense an input voltage V in, and what we produce as a function of that input voltage, we produce a current, an output current. And so this gain, which is called the transconductance GM, is the ratio of how much output current you get as a function, as a ratio with the input voltage. Now, since we have a current amplifier at the output, the maximum output current is going to occur when the voltage is equal to 0 or the load is equal to 0, right? It's a short circuit. And so with that, what will we want? We will want that in the input, Ri, in ideal conditions, will be infinity, okay, so that you do not drop this input voltage at all if we connect a source. And at the output, we will want the output impedance to be infinity, because otherwise, once we connect the load, we are going to have a current divider. Now, you use this to do any voltage control current source amplifier, but also this is a good model for BJTs as well as for MOSFETs. So you want a general model for all types of transistors, the transconductor amplifiers works for that, where you can say, as a function of a voltage between two terminals, I get a current somewhere else, okay? The voltage between the base and the emitter produces a current in the collector in the BJT. Or similarly, you can have in the MOSFET with the MOSFET terminals. Last one, transresistance amplifier. Okay, so in this case, what do? We sense a current at the inputs. II. And what we produce at the output is a voltage. This voltage is a function of the open circuit transresistance, which is the gain, and the input current. So the transresistance, Rm, is defined as the output voltage divided by the input current, and this is done because you don't want the output voltage to be loaded when RL, the load, is infinity, RL equals infinity, or the output current is equal to 0, meaning you left it open. So that's the definition right there. And ideally, what do we want? Ideally, we want that the input impedance is 0, because we want to sense that input current and you don't want the current to become smaller because of that input impedance or have a current divider effect. And the output impedance, you wanted 0. So those are the ideal conditions. Okay, so let's do a quick review. And this is, I should say that this is what? A current control voltage source. And you will model all that sort of amplifiers. Okay, so in a voltage amplifier, we have the open circuit voltage gain. Ideally, we want an input impedance that's infinity, and output impedance that is 0. In a current amplifier, we have one current at the input, which we want to amplify it at the output. The short circuit current gain is the ratio of the output current to the input current. What do we want? An input impedance that is 0, an output impedance that is as large as possible. So anytime that you have a current amplifier, you want current amplifier with a high output impedance. Transconductance amplifier. You sense an input voltage and you produce an output current that is a function of that input voltage. And so you want ratio of output current to input voltage. That's the transconductance. And that's the transconductance in short circuit conditions, because you want to do this when the output voltage is equal to 0 or R is equal to 0. Ideally, what do you want in a transconductance amplifier? You're sensing an input voltage, right? So you want an input impedance that is infinity, and you're producing an output current, and in the output current, you want the output impedance to be infinity. Finally, in a transresistance amplifier, what do we have? At the input, we have a current, and based on that current, we produce an amplified voltage by a factor of the transresistance, which is the open circuit transresistance, since the output current is equal to 0 or the load is infinity, meaning you disconnect the load. Effectively, anytime that you have a voltage that you are sensing at the input, what do you want? Input impedance that is as high as possible, infinity. Anytime you have a current at the input that you are sensing, you want input impedance as close to 0 as possible, 0. At the output, anytime you have a voltage, what do you want? Output impedance, 0. That can be the voltage amplifier, or that can be the transresistance amplifier. Anytime you have a current source at the output, whether it is a current amplifier or a transconductance amplifier, you want an output impedance that is as large as possible, so you do not have a current divider at the output. I think that with this, we completed the activity. In general, I should mention that if you want to find the input impedance or the output impedance in any circuit, right? You have a circuit. Let me maximize this here. So we have a circuit, a block, and we want to find the input impedance. All right, what do? We can just go ahead and connect a voltage input and see how much current II is going to draw, and the input impedance is going to be VI over how much current it drew, right? Similarly, if we want to find the output impedance, what can we do? We pick that circuit, disconnect all the sources, put a test voltage at the output, Px, look at how much current the circuit draws, and our out is going to be Vx over Ix. Remember that we need to disconnect the sources, so de-energize the circuit. Thank you.